All right. So, as for what we're doing this week, it's going to be a bit more complicated. Someone acknowledge that they can hear me?
Yeah, we can hear you.
All right, good. I think Kevin, you're good to be on server muted now. All right. So, where am I going? I'm going here. All right. So today's lesson is going to be a lot more challenging this time around, and it's going to be binary search and introduction to segment trees. So I'll bet that most of you, well, as per the poll from last week or a bit of time ago, let's check. Let's check actually. So 8 of you are familiar with binary search. Oh, no, that is not the right poll. Are you familiar with binary search? 12 said yes, 15 said no. But we're going to go through it anyways. So, the idea of binary search is that it's searching for an element in an array, and it's done in big O of log n time, which means that it's remember log here is log base 2, and it's primarily used to find an element in some sorted array. And the idea is that it's a warmer or colder game. It's like you start with a huge array of locations where you're trying to find the right one. So you pick. The objective of the game is to guess a number while minimizing the number of tens. If the guess is right, then the game is done. Obviously, once you find your element, you can just break out. You found the element. Yay! Woohoo! We're good. Otherwise, if the guess is smaller than the hidden number, then the response is colder. And if the guess is greater than the hidden number, we're going to say the response is warmer. That's going to be the slight tweak that we're going to have to the warmer colder game. So in short, what we're doing is we're essentially going to keep looking and seeing if it's greater than, warmer, if it's less than colder. And another example is finding a word in a dictionary. Normally what you do is, one way you could do it is obviously just go through the first letter, find all pages, find the starting page with the first letter. Let's say I'm looking for the word carrot. So I'd go to the first page that has the letter C, so I know where to start. Then I say, what's the second letter? Then my second letter is A. And then, so that means it's relatively early in my range of pages that have C's. And now I look at the next character as R, so that means I have to go a bit past. What the heck? So I have to go a bit past because I don't want to do like CA and anything like higher than R. I want to go R or I want to be close to R. So that's one way to do it, but that's going to be more efficient in terms of the dictionary way. But another way to go through it is to bisect the dictionary in half. So let's say I have all the letters of the alphabet. Do I type them out real quick? Sure. A, B, C, D, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Okay. So bisecting them, I'm going to get M or N. So I think it's M. I'm not sure. So so I'm going to bisect and look at where M is. And I'm going to say, wait, so is M going to be the one M going to be the one that I want? And it's no, obviously. But so is it to the left side or to the right side? Since I'm still working for the letter caret, it's obviously going to be to the left. So I'm going to bisect and use this half. So that means I can eliminate this second half. Is there a strike through here? Yeah, strike through. So I can eliminate that second half because I know it has to be, the starting letter is greater than or is less than M. So now I look at A, B, C, D, E, F, G, H, I, J, K, L, O, M. And I think the bisection is G. Correct me if I'm wrong. Yeah, the bisection here is G. So look at G now, because that's bisecting this segment from A to M. So I check. Now, is my letter G? Obviously not. So that means I have to go either to the left of this segment or to the right of this segment. And obviously, since we're looking for C, we know that C is less than G. in lexicographical order or alphabetical order per se. So that means I'm going to have to go to the left. So that means the right side here is going to be taken out. And I also made a mistake. When I first eliminated, actually, going back to here, when I first eliminated, I had to take out the M. I should have taken out the M2 because I know it's not in there. So I actually should have bisected. I should have taken out M when I was striking through. So now I had A, B, C, D, E, F, G, H, I, J, K, L, and we determined that it was G. And because that might not be perfect division, but we'll just go with it. So there's A, B, C, D, F. It has to be in that range. So that means I can cross out this right side. Now I'm going to go A, B, C, D, E, F. That's a length of 6. A segment of length 6. That means I have to go to the third one, and that is C. And so is C our desired one? Yes, because we're looking for the first letter of caret, which is C. So that's the one that we're going to choose. And a similar idea. We see that we were able to cut off one segment and then another segment, and then we got to our third segment. But the reason why it's the time complexity, this is the basic idea of binary search, but the reason why the time complexity is O of log n, because the worst case scenario is that you bisect once, and now you have to check the other half, then you have to bisect again, and then check the other half, and then bisect again, check the other half, and so on and so forth, until you get to the fact that there's only one element, and you can't bisect one element, which means that that's the one you're looking for, had you implemented the binary search correctly. And so essentially you're doing the worst case time complexity is how many 2's divide into the number n. In other words, the time complexity of that is O of log n, because log in computer science is log base 2. Any questions about binary search? No? Okay, let's go ahead and implement it. So, let's actually try to do it ourselves instead of looking at the source code on the bottom here. And I can't type. I should probably zoom in. All right, can people see that zoom level? The code?
Yes.
Okay. So obviously we're gonna have to include bit/std++.h using namespace std in its main. Now, let's say the given problem is you're given 2 lines of input. The first line is n, the number of numbers, the number of elements in our array. The second line is t, or m, the desired number that we are looking for. And with m and n, what we have to do is, using binary search, figure out how many cuts or how many operations, or let's say how many segments or bisections we have to take to reach m. In bisections with binary search, with the elements of the array of the numbers 1, 2, I don't know why I turned the caps lock on, 1, 2, 3, ... to n. So a sample input is 26. All right, actually, let's go ahead and do an example ourselves. Actually, you know what? I feel like it's straightforward. Binary search, figure out how many of the bisections with binary search that you have to do with the elements of the array 1, 2, 3, ... to n, which is the first line of our input, and we have to take to reach m. So in other words, this question is asking you to simulate binary search and figure out how many times you've bisected. So let's go ahead and do that. So ints n and m. Take input, and I'm not using fast input because I don't think that's necessary. That's definitely not necessary for this problem with only 2 inputs, and this is also just a test problem. All right, so take in inputs n and m. Now we have to now we have to actually work something out. How are we going to store what segments we're currently looking at? Like, in other words, if I have 1, 2, 3, let's say n was 5. That means, or let's go 6. 1, 2, 3, 4, 5, 6. So currently, at the very first step, we're going to have to look at the entire array. But, okay, so actually, you know what? Let's just actually do a sample input. That's probably better. 6. Our first letter, n, is 6. So that means elements of the array are 1, 2, 3, 4, 5, 6. And then we are looking for the value, we're looking at trying to find 3 in the array. And we're asked to find, obviously, how many bisections you have to do to find the element. So first, we take our array 1, 2, 3, 4, 5, 6. Now, if we bisect it, where are we going to be at? Someone give an answer. Anyone?
It will be element 2.
Are you 0 indexing?
Yeah.
Okay, yeah. So, since we're 0 indexing, that means we're going to be at the left side is 0, then 1, 2, 3, 4, 5. So he's right, because we have 5, and we're going to split it into 0, 1, 2, and then 3, 4, 5. And we'll see exactly how the splitting is implemented. You could probably take a guess at it, but because I've already given the hint that it's a binary search. So we're going to split it at element 2. And at element 2, our value is 3. And that's what the value that we were looking for. So that means that we only had to bisect once, which is what we're looking for. So that means our output would be 1. Now, that number that happened to work out too well. So let's try the same n value.
Yeah, we can see your old code on the right side.
Yeah, I don't care really. That was just testing, and I screwed up. So you know what? Yeah, let's just put that on the side. All right. So this time we're looking for the element 6. All right. So we're starting off with 0, 1, 2, 3. The index is 0, 1, 2, 3, 4, 5. And now we have to do our first bisection in the binary search. So now, as Kevin pointed out before, the bisection is going to be at this element over here, because it's how it works is it's halfway between the indexes 0 and 5 is 2. And yes, we're just going to do integer division because that just makes life more simple, because I don't want to deal with index 2.5 not existing. All right, so elements, how I did that was you take the average of the two numbers of the current left and right, and then 0 plus 5 is 5, so 5 over 2 in just integer division, that's element 2. So element 2 is 3. Our desired value, m, is greater than 3, so we have to eliminate indices per se 0 to 2, because now we know it can't be in the first half, because since this is in sorted order and m was greater than 3, that means that means it has to be on this right side. So now we split split the array, and or actually eliminate indices 0 to 2. Remaining is 3 to 5. And instead of actually, yeah, let's just keep going with it. So our remaining is 3 to 5. Now we have 4, 5, 6. And I'm still going to use the same indices of 3, 4, 5 because there's no point in changing anything if you don't have to. Now we want to bisect this. So someone tell me, someone different, not Kevin this time. If I had to take the average of the left and right, what would I get to use as a bisection? Anyone give it a shot? Remember, there's nothing wrong with being wrong.
Or?
Yeah. Element 3 plus 5 over 2 equals 4. And element 4 in our array was 5. And now we have to check, and obviously we know that m is greater than 5 because our m value is 6. So we have to eliminate the left side, which is anything below index 4 and index 4 itself, because we know it's not possible. So indexes 4 to 5 are gone, and remaining indexes are 6 to 6. And now at this point, we know that its element, our element here is 6, and as index 5. And since we're looking for the value 6, and there's only one element in the array, so at this point, if you haven't done anything wrong with your code, if there's only one element, you've already done your binary search, and you found that it guarantees to exist, then it would be fine. All right. So, but however, elements 5 plus 5 over 2, because left and right are equal now, is 5 is 6. Target found, and we did 1, 2, and then there's no bisection here really. Well, I guess it was a bisection. No, we didn't bisect because we did a bisection here and a bisection here. So output 2 for a number of bisections. So our final answer would be 2. However, as I hinted at earlier, if there's only one element in the array, you have two possibilities. That's the element you're looking for, and that's the one that you want to output. Or if you're trying to find the exact element, and this value is still not there, then that means you've guaranteed that the element isn't even the array in the first place. Like if I was given 1, 2, 3, 4, 5, 7 as my input, or as my array, searching for the value 6, we know that it's not going to be found, obviously, because we can just look and see, hey, it's not even in the array, what are we doing? But if you did your binary search with the same process, because the first elements are the same, so you're going to bisect this part away, then you're going to bisect this part away, and then, no, not that, and then you'd be left with 7, which is a dilemma because you're looking for the value 6. And that means that the value 6 is not present in the array. So that's the idea of binary search. So assuming that we're sticking with the same problem, let's go ahead and try coding it. So we have our M and N input. So we take input for M and N, and so that means that we're looking in the array values in the array 1, 2, 3, 4, 5, 6. And just to visualize it, let's create a vector of integers from 1 to n. We don't or actually an array of integers from 1 to n. but we don't have to, but let's just do it anyways. So int r, and Replit might not cry. Okay, Replit doesn't care that some other compilers would have problems with the size being a variable, but apparently Replit's fine with it. So let's assign all of our values. For int I equals 0, I is less than n, I plus plus. And we know that the index 0 had a value of 1 originally, and that's how we're sticking with the same problem. So that means that array of I equals I plus 1. And so now we're filling array with values 1, 2, 3, ... to n. So after we fill the array values, now we have to go ahead and do our binary search. Looking back here, we had a value on the left side and the right side. And here what we did is when we bisected it, we moved the left side to, notice how the middle was at 2. And then after, because the value is greater, we moved it to we moved the left side to 1 above the middle. And then similarly, the middle was 4. We knew that it was greater than 4, or the value was not was greater than the one at the bisector. So that means we moved the left to 1 greater than 4, which is 5. And then here the left and right were both 5. So that means with the same idea, we want to have left and right variables. You can do LR or left right. Let's just use left right so no one gets confused. And originally, it was the left was at 0 and the right was at 5 because those are the bounding indexes that you could use. So left equals 0 and right equals, and since it filled with a spot of n, then that means the index is n minus 1. The rightmost index is n minus 1. So now we have to actually go and do our binary search. And first we'll assume that m is... Alright, so let's first assume that m is guaranteed to be in the array. So if we're guaranteeing that m was in the array, then we could just go ahead and just do a regular bash, try to find it. However, we need to keep track of the number of bisectors or bisects that we've done. We did one here and then one more here. Alright, so int bisects equals 0 because we start off with no bisects, obviously. That's not good. Alright. So we want to keep going until we find the element of the array. So what type of loop or structure should I just start off with? Because I know I want to keep going until like the left and right match out so that the bisecting index works. What type of loop, what type of what should my approach be? What type of loop, first of all?
You need a loop.
Which type of loop? Is it a for, a do, a while? Lily, what do you think? What type of loop should we use? If you don't know, can you at least acknowledge that you're here? Nice. Someone else. Let's see. Rayton, what type of loop should I start off with here?
While loop.
Good idea. Good choice. That's what I was thinking as well. So let's just go while true. At first, we'll do the while true because we know that if m is guaranteed to be in the array, then we can just keep going until we find m. So now we have to actually find our our middle index, because the first thing we did over here was we found the middle index by using the left plus right over 2. So let's just use the same process over here. So int mid equals left plus right over 2. And now, we obviously want to check, is this the element that we're looking for? Because if so, we don't need to bisect. We don't need to find anything. We can just say we did not bisect this time. We can just print out the number of bisects. So if mid, or if our array value at the middle index is equal to our desired value, which was m, then we want to print out, hey, we found m. We found it in this amount of steps. So cout, we found m in and then obviously we're incrementing with the number of steps being bisects. Steps. And I'm just gonna put an endline character. So we found it, and then we don't need to do anything else, but we have to escape the while loop if we found our element. So that means we have to break out of it. So hey, we found it, we're good. But if r at mid is not equal to m, that means we've clearly done something wrong, or not necessarily done something wrong, but rather it's the point that we bisected at is not the element that we're looking for. Which means there are two cases. One, if array at mid was less than m, and then you don't have to write else if because we know there's only one possibility, but we'll just do it anyways. If array at mid is greater than m. So now we're in this problem where we've found the bisection point in the array, but yet the value that we're looking for is less than m, which means that it was the same problem over here where we bisected, we found that the element 2, the element at index 2, which is the value 3, was less than 6. And as a result, we had to make our left side one above, we had to eliminate everything from the middle point to anything to the left of it. Or in other words, instead of eliminating or removing from an array or something like that, what we can simply do is just make the left value 1 plus our middle value, because then on our next thing we have 3, 4, 5, and then our desired elements 4, 5, and 6. And here we're not considering the 0, 1, 2, because when we take our average left plus right over 2, there's no way that it can be less than the left side, because because taking an average is going to be between the two numbers. So that means all the indexes 0, 1, 2 that we had above here, they're not going to be relevant anymore, but we didn't necessarily delete them. So we're going to do the same process. If array at mid is less than m, now we have to bring the left side equal to mid plus 1. And here we cut off the left side, namely the range from old left to the mid. And these square brackets mean they're including the values itself. So we're cutting off everything old left to mid, the range old left to mid, and including both ends. And then otherwise, which we found up here. Wait, no, we did not find that up there. We found it actually in our Word document, where we were looking for the element C, and let's just unstrike through all of those. And we said our middle value is m. I'm not sure if that's completely true, but let's just say for the sake of it that it is. We cut off everything from the middle to the right. So that means that our new right side became 1 less than what the middle value was. So that means we can simply do right equals mid minus 1. And what happens is, now that you've reassigned your left or right, because it was either we cut off the right side or we cut off the left side, let's actually write that off here. Namely, mid, comma, old right. we cut off. Let's say that we went here and let's use a previous input. We changed our left to this one, and now we have to go back into the while loop again and find our mid, because that's what we're trying to increment. In other words, no, not what we're trying to increment. That's the value that in which we're trying to use for the next bisection. So in other words, we bisected here, and then we've done all of our things. We've done our case checking. We've reassigned the left or the right, and now we can check that half segment compared to the previous one and see where is it in here. And so obviously I screwed up. It wouldn't be me if otherwise. And over here, when I've actually checked these cases, that means I'm essentially going to bisect the array, which means that over here I can just bisects plus plus. And if I wrote plus plus bisects, let me just go through this real quick because this might get some people curious. Bisects plus plus versus bisects minus minus. The effect of putting plus plus is it'll do all the operations on one line and then change the bisects to one more than what it was. But rather over here, if I do plus plus bisects, then that means it will add one to bisects and then perform all the operations on the line. I might go into more explanation there later on, but that's just a simple idea for those who are curious. So I've incremented our bisects value, and so assuming that m is guaranteed to be in the array, that means it will eventually get to this there's mid value for which array at mid is equal to n. So we don't have to do anything breaking here because we know it's going to go into the while loop, and if m is guaranteed to be in the array, that means at some point array at mid has to equal m. And let's go ahead and see if that works. That's probably really zoomed out. Give me 1 second.
Is there a reason why you want to use one over the other, or is it just preference?
For the plus plus or like...
Yeah, the postfix and prefix. And...
You know, I'll actually talk about that in a second. Just give me some time. Let's finish this first, and then I'll talk about that because that's actually a good question. You can always do every operation with one, but if sometimes you wanted to change you change a value before you want to create your operation, then it'll be beneficial to use plus plus bisects. It'll save a line at most, but sure. Let's just go ahead and go with it. So we've already said that if we did a simple input of 6 and 3, that actually this output should be 0 because we never bisected the array. We never actually cut off anything in the array, so this is 0. So if I put 6 here, nope, 0. If I put 6 here and 3 here, see, we found 3 in 0 steps because we bisected it. We cut it in half once, but we didn't chop off the other half, and so we found it in 0 steps. And if we do n is 6, m is 3. No, not n is 6, m is 3. If n is 6 and m is also 6, we found 6 in 2 steps, or 2 bisections. I should probably change that to bisections, just so no one gets... Or cuts. Let's go have cuts. Since we cut it once here to eliminate the left side, and then we eliminated the left side again, and so we were left with only one value of 6. So we found 6 in 2 steps. And we'll see that if we make the size really big, like 1,000, 10,000 even, and then we want to search for elements 9,900 or 9,765, I don't know. We found 9,765 in 13 cuts. Normally, if you just went through every element, you would have found 9,765 in 9,765 like tries. Like you had to do that. You have to search every element through a for loop, check if that's the right one. If not, you have to move on to the next one. So you had to do that 9,765 times, and rather, here we did it in only 13 cuts, which is so much faster. So obviously, if I went even bigger, which at a point the stack size would be too big, but let's see how much we can push Replit. 100,000. I don't know how far I'll go. Let's go 67, 678, 5, 4, 2. We found it in 15 cuts. And that's so much faster than doing 678,542 cuts. And here we see that it's so much faster because we increased by a factor of 10 and our number of cuts went up by 2 from 13 to 15. So obviously you see that as n grows really large, and our log n value, our number of cuts, is going to grow unless you get lucky and you cut it at a point which is the perfect value, or otherwise you'll end up with O of log n cuts. And we obviously see now that O of log n grows a lot slower than O of n does. So worst case scenario, if you just did a regular for loop, is O of n, or in this case 1 million. But with binary search we found in 15. Now obviously we found m as no, not m, my bad. We were doing it with just the numbers 1, 2, 3, 4 ... to n, in which you might think, hey Zach, can you just find I plus your index is m plus 1, then you just you found a number already and that was just one operation to find the number? Yes, but remember, this was just one example with the values 1, 2, 3 ... n. What if there were values that you didn't know and they skipped numbers? Like what if it was 1, 2, 4, 7, 65, 127, 230, 245, 1,000, 10 million, and it just kept increasing in random order. And that's where the beauty of binary search is there. I hope that makes sense, that in this specific example, you could cheat off of it and just say, hey, it's I plus 1, you found it in one operation. But in reality, when you take input and they're just wacky numbers, you just sort them, and then you just perform binary, assuming they're sorted, actually. And then you can just find it a lot faster in O of log n time rather than, worst case, O of n time, which is really, really slow as n grows large. So any questions with what I've done so far with binary search? Remember, don't be afraid to ask. It's better to ask, quote unquote, embarrass yourself, if you will. It's not even embarrassing, really. Being curious is one of the better things you could ever do. Okay, and then there are different aspects that I'm not necessarily I don't think I need to go into. Like, if m was not in the array, then you keep searching until the segment is 1, the size of the segment is 1, and if the size of the segment is 1, or in other words, left and right were the same, then you would say if r admit equals m. But if not, but left and right were both the same, that means that it doesn't exist in the array. And then you could say, you found it really fast that the element doesn't exist. And then there are other approaches other things where you can do, like find the first element that's greater than this value in the array. And then and then you have to change the code slightly to somewhere over here. I think you do something like if r admit is greater than or equal to m, or something like that. So there are different approaches to different problems, but this is the general idea of what binary search is. It's a very, very beautiful concept, I believe. So yeah, if there are no questions, then I'll go on to segment trees. But before we necessarily go on to segment trees, we're going to have to talk about, because in my opinion, there are a lot of wacky ways to implement the segment tree, and I think honestly that there's some really good ways, but there's also some really bad ways to implement segment tree, and the best way, which from what I've like, the most logical way to learn the segment tree has to involve something called structs in C++. They're essentially classes, but they're not. They're weird at first to implement, but then they become simple and intuitive. So we're gonna go ahead and do that for now. Let's create a new REPL. CSC week 6 R2. Refresh my page. All right. Using namespace std int main. Okay, so here's the thing. Sometimes you know that sometimes you can declare things quote unquote globally in C++ by putting them outside of int main, or you can declare constants, or you can do macros, or you can do use functions for that matter. Those are common to many programming languages, but the idea of what a struct is for, I don't know, actually I should make a poll. How many people have not taken or have not taken or have not had yet the course ICS 3U?
I already do this before.
Pardon?
Wait, I can write it. I can write it for you.
I've already. Okay. I put it in your polls. I want to know if there are a decent amount of people. Oh. Wait, have not taken. Wait. Yeah, Samir, you're in my class. Kevin, get your name off of there. Alright, looks like I'll forcefully delete his reaction. Alright. Okay. So Marco so far. Relatively young kid. Not to make fun of you, Marco. Alright, but we'll just go through as an idea of what a class. Alright, we'll go through what the basic idea of a class is. A class is is something that holds.
Never mind.
That what?
No, I was gonna say the poll was kind of ambiguous, but never mind.
Okay, but I'll just go through. It's not going to take too long because it's not wacky like in graphics or something like that. Alright. That holds objects that have certain properties. I cannot talk. I can't type. A class is something that holds certain objects, or that has objects that hold certain properties. For example, every person in Comp.Sci Club is has the following properties. Either wears glasses or it does not wear glasses. Someone give me another example.
Age.
They have a certain age. anything that's common with all, like a property that of every member of ComSci Club. Anyone. We need to get a lot here.
Male or female or
Well, okay, gender.
gender. Well, gender in general, I meant.
Yeah, well, you can't say male, female, indefinitely. Anyone, give me a lot more.
Wait.
Wait.
Grade.
Great. All right. So other people besides Gordon and Kevin. Height.
Preferred language.
Wow, now you answer Lily. Were you always here, or did you miss out on a little bit? Because I did call on you before and you didn't answer.
I was always here, but in the beginning, like, my mom was talking to me, so
Oh,
I didn't hear.
At least it wasn't
Yeah.
UC. Anyone else? We have a good list so far, but
They're marking computer science.
that's assuming everyone's taking computer science, and by the polls, that's not necessarily true. So we cannot say that. Eston, give an example or something that we can put as a property.
I mean, I don't know who drinks coffee, who drinks tea, who drinks water. I don't know. What's their
okay, yeah.
preferred drink? Yeah,
Preferred
sure.
drink.
Why not?
Okay, so yeah. Okay, we see that the object's called. I'm not trying to objectify you guys, but I'm objectifying you actually. We all either wear glasses, do not wear glasses. We have a certain age, certain gender, weight, grade, height, preferred language, preferred drink, and the list goes on for so long. So the idea of what a class is that it holds certain properties, and then each object has a certain value in each of the properties. So let's say I was an object, then the Boolean of whether I wear glasses or not is true. The Boolean of whether I swear not Boolean. The integer of my age is 16. My gender, male. Weight, I don't know. I don't have a scale, but let's just say like 150. Or wait, technically FG equals MG, so I don't know my exact weight. Grade 12. Height 5'6" or 5'7", I have no idea. Preferred language, English. Preferred drink, water. I as an object have these have certain values attached to these properties, and that's what essentially a class. Every object in the class is going to have certain values attributed to these properties. So now, so that's essentially what the basic idea of a class is. So C++ struct is very similar to a class. The only recognizable difference or differences are syntax and security, whether something is private or public. And you don't necessarily need to know about that for comps, or what private or public or protected mean for ComSci Club. You will need. I think that Mr. McKenzie still teaches it for ICS 3U or ICS 4U, despite the fact that the curriculum got cut short, unfortunately. But so these syntax and security, where the syntax of a C++ struct is so much easier to understand. There might be some other things. Always ask Kevin Zhang as your local C++ guide if you ever need to know the differences, but I don't think that you need to know the differences. So we're just gonna move on. All right. So how it's a struct is made in the following. It's made in the following method. So you have the struct and then name of your struct, and remember, don't put angle brackets in these areas. And then here are the list of properties of elements in the class or objects in the class. And then over here, you can have certain containers or values predetermined that are predetermined as elements or predetermined as objects, and then you end off with a semicolon. Now that is going to seem so confusing to you guys at first, but we're going to actually do an example. Okay, so example 1. Struct named CSC member. Alright, CSC member, let's go with that. Properties, we're just going to go simple. Wears glasses, true or false. Age as a number, and we'll go preferred language. And then we'll have predetermined, let's go with predetermined objects are going to be, who wants to volunteer as their names to be in here?
Me.
Kevin. Anyone else? Evan, and I'll just pick one other person, Joshua. So let's go ahead and write what the structure looks like for that. Struct, remember, struct, and then the name of the struct, CSC member. And now we want a boolean of wearing glasses. So bool glasses user, sure. Bool glasses user, int age, and string preferred. I do not know how to spell preferred lang. So simple. Everything up until now is simple enough. You just put all your properties in the class. You don't assign values inside of there unless that's a predetermined thing for every element of the class, which I don't see a scenario in competitive program where you need that. And we determined that Kevin, Evan, and Joshua are predetermined objects, and then we have to end off with a semicolon. That is the most annoying part about a struct. I don't know why you have to end up, well, it makes sense why you have to end up with a semicolon, because if you put things here, then you need to have something to show that there's an end to your predetermined structs. So struct CSC member, and then we have bool glasses user, int age, string preferred language. Now let's go ahead and assign some values, or assign some things to them. Kevin dot, and that's the way you access them is Kevin dot, and now you can just put glasses user. Kevin, do you wear glasses?
I do not.
Equals false. Kevin dot age equals Kevin.
I am 17.
And what is your preferred language?
English too, I guess.
English. So pretty simple. Just object dot the property that you want to modify, and then you can just go ahead and change it. And then you can access it at any time. Kevin dot glasses user. Actually, sure. Let's just Kevin dot glasses user. Let's go ahead and see what happens when I do that. Run. 0. So why did it print out 0 and not false or true? The reason is because every boolean is either yes or no. 0 for no, 1 for yes. Like a light switch, on or off. And in C++, their default is stored as 0s and 1s. So that's just a wacky thing. When you output a boolean, it's not going to output true or false. It's going to output 0 for false or 1 for true. That's just how it works. But if that's not going to change how if I put Kevin.age, it's not going to print out 0 or 1 or anything like that. It's going to print out 17, as you will see. So we have Kevin.age is 17. Simple enough. Now let's modify this. Now let's modify So we can always assign, reassign, blah, blah, blah. And notice how I said certain containers or values predetermined as objects. So I can actually put a container, or we can put an array for an example, like weird people and size 5. So now there's an array of size 5 called weird people, and each of them is a CSC, as it belongs to a CSC member class. So if I do something like weird people at, let's say, index 2 dot age equals I don't know, 15, sure, I can go ahead and do that now, and I can access it at any time. So so you can put any container in there, and you can put any container of value as predetermined things. But if there's a you don't have something that's predetermined, not predetermined, you essentially treat it as a type. Like if you, let's say you want to create, when you want to create an integer name with a variable name of Joe, you just go int Joe, right? Similarly, you can do CSC member. And anyone else want to volunteer?
You can use my name.
CSC member Lily. And so I didn't have to predetermine that Lily is going to be a CSC member. She just randomly popped in. And now I can do the same thing. Lily dot classes user equals, I don't know if Lily was classes. I'm just going to say false. Lily, correct me if I'm wrong.
I wear both contacts and glasses, so it works.
All right, sir. So you're saying it's false, true and false.
Yes.
All right. So Lily.glasses user is false. Lily.age is, I'm guessing it's 16. Lily dot preferred lang, what is it?
English.
So it's very, very intuitive compared to languages like Java or something like that. So that's the idea of what a struct is. It's very straightforward. You just do object dot property that you want to modify. You can modify as much as you want. So that's the idea of structs. And remember, always have the comma, always have the semicolon at the end, even if you have no predetermined things. If I want to do like struct keys and in int num for example, if I don't have any predetermined keys, I still have to put a semicolon at the end after that. That's pretty weird, but because it's just trying to detect that, hey, there's nothing here. Now I can just end off because I know there's a semicolon, so I don't have to worry about the struct. That's what the compiler's thinking. So now we have to go into the segment tree, now that we have the knowledge of a struct. And this is where the big part of today's lesson is going to go. Now, I don't expect you guys to fully get this or comprehend even half of it. But it's going to take some time, and so that's why I wanted to give you an introduction to it. All right, so we found the struct, blah, blah, blah. And there's going to be some more examples up there. Okay. So going back to this Word document. So with a binary search, we were able to find the location of one element, or we were able to do something with one element in a sorted array. But what if you want to do something with a range query? Or in other words, I want to pull an operation on multiple arrays, or multiple elements in an array that are in a range, like query left, QO to QR inclusive. And I don't want to do it in a time complexity of O of n. That's what the segment tree is going to be used for. segment trees allow us to do some queries in O of log n, which is really, really fast compared to O of n, as we saw many minutes ago. And so we can eventually span other tasks in a segment tree, along with, let's say, we want to do the minimum, finding the minimum element in a given range, or MRQ, which means minimum, or this could also stand for maximum, but minimum range query. So we want to think, how can this work out? Let's create an example. Should I use whiteboard? Okay, yeah, let's use whiteboard. All right. I don't know how well this is going to go, but I'll give it a shot. So let's say I have the elements 1, 3, 7, 9, 15, 30, and 45. And let's go more, actually. 16. Now, these are not necessarily sorted, but these are going to be in random order, as you're going to see. And 14, 1, not 1, let's go 7. Actually, we did 7 already, too. Let's go 6, and 15. No, not 15, 18.
Wait, it has to be unique?
No, but I'm just giving an example so no one confuses it.
Okay.
Segment trees do not have to have unique values. So let's say I have this weird array, or any array, for example. But let's just say I have this array. Is a size, let's just index these. 0, use a different color. 0, 1, 2, 3, 4, 5, 6, 7, 8, oh my god, 8, 9, 10, and 11. So there are 12 elements in this array, indexed from 0 to 11. And now the question is, minimum range query. And our desired time complexity is O of log n. So how can we do a minimum range query? Let's say I want to pick the elements 4 to 10, and we want to find the minimum of those elements. What's the minimum range query? So obviously, the obvious approach is start at index 4. The current minimum is just this first element, 15. We go into the next element. The minimum is, we can change the minimum to 30 or use our previous minimum because we're looking for the minimum of all elements. And clearly, 15 is less than 30. So that means our minimum out of these two elements is 15. Then check the next element. Is it greater than 15? Yes. So that means the minimum is still 15. Then 16. Yes, it's still greater than 15, so the minimum is still 15. ... You get over here, you see, 14 is less than 15 now. So that means my minimum this entire so far has become 14. And then finally, our index 10. Now this has become this element has a value of 6, which is less than our current minimum of all the other elements. So that means our minimum becomes 6, and that's all the elements from 4 to 10, inclusive. So that means that the minimum of all elements from 4 to 10 is 6. Now, do you notice how I had to go through each element and check what the minimum value was? And if the value was from 0 to 11, I'd have to go through literally every element in the list, or in the array, and find out that find the minimum value that worked. And as you can see, that is very, very slow as n gets large and you want to do multiple queries. Sarah's taking a sip of water there. So yeah, we know now that we can see that it's already really slow, and I'm going to introduce a way that does it in big O of log n. So let's think about it. A hint here is that it's very similar. Let's work on the idea of it's like binary search, where if we want to find an element in the array, we're able to do so in O of log n time. So let's create a tree. And this is what the idea of the segment tree is. let's create a segment tree. Okay, our first element is going to be, let's deal with ranges first. Since we know that, since I've introduced it in a way that I'm saying that we can do an O of log n, then that means there's some idea that we're going to have to do some cutting in half and comparison and blah, blah, blah. So let's go ahead and let's have this range over here, 0 to 11, which is from 0 to the size of the array minus 1 of what we're dealing with right now. 0 to 11. So what can we do with this? Actually, let's not worry about what we can do with it. Let's say that every node or every index in a tree, well, not node, no, not index, it's a node. Let's say every element, or not every element, why am I keeping going like this? Every node in the tree has 2 children if it can be bisected. And the 2 children, child of node with range L to R have ranges L to mid and mid plus 1 to R. Essentially what we're doing is we're cutting the range in half and assigning the first half of the range to one node and then the second half of the range to another node. Notice how this is very similar to what we did in binary search, and that's why I wanted to introduce binary search. So we had this idea of splitting in half and then dealing with the halves of themselves. So let's split the from the range 0 to 11 in half. What is the mid index that we're going to deal with from if the left was 0 and the right was 11? Note that that we do it from L equals 0, R equals 11, and we determine our mid to be left plus right, integer divided by 2. Zero plus 11 over 2, integer division, or floor division, if you want to do it like that. This represents floor, which means the greatest integer less than what or less than or equal to our current value, because we obviously want to round, division rounds down in C++. So actually, I'll just go ahead and do it. So 0 plus 11 over 2 is 11 over 2, which is 5.5, but since we're doing integer division, our value is 5. So we want to cut it, our mid value here is 5, and we want to cut it so that the left takes on the old left, and our right value of the new node is the mid. So that means our left child over here is going to be 0 to 5. That's a very weird squiggly. 0 to 5. And then this child over here is mid plus 1, or in other words, 5 plus 1 is 6. 6, 2, and then we keep it as 11. And notice how when we divide it like this, 0 to 5 and 6 to 11, if you were to combine those two, you would get that. Like, if you were to combine the elements from 0 to, like, the indexes 0 to 5 and 6 to 11 into one thing, it's just 0 to 11. So in other words, we just bisect the segment, and split it into 2 segments. L to mid and R to mid plus 1. So now let's go ahead and keep dividing. Let's take this child over here. Or this is going to be a parent of 2 nodes. 0 to 5. So that means we're going to have 0 plus 5 over 2. And when you do 0 plus 5 is 5. And then you integer divide by 2. 5 over 2 is 2.5. But when you divide with integer division, the middle value becomes 2. So that means that our mid is 2, so that means this left is 0, because we're inheriting the left from here, and then the mid of those two is 2. So 0 to 2, and that was weird, and 3 to 5. Now let's come over here. 6 to 11. Same process. We have to do 6 plus 11 all over 2. And take the integer, we have to round down or to take the floor, per se. Integer division. 11 plus 6 is 17. 17 over 2 is 8.5. And we round down to 8. So that means we're going from here is 6 to 8. Because we're inheriting the left value and we're taking the mid because it's L comma mid. And then mid plus 1 comma R is their other child. So that means we have to go 8 plus 1 is 9. And then our right value over here is 11. And same process over here. We have to go L plus 1. No, not L plus 1. L comma mid. And then mid plus 1 comma R. So the middle value here is 0 plus 2 is 2. 2 over 2 is 1. So that means our mid value is 1. So we have to go 0 comma 1. And 2 comma 2. And notice how here we have a left and right that's the exact same. We're going to explain what happens when we get there when we divide all the other stuff on over here. So 3 to 5. 3 plus 5 over 2 is 4. No integer division or flooring needed. So we have 3 to 4 and 5 to 5. And then over here, when you divide it, 6 plus 8 over 2 is 7. So that means this one is going to be, let's make it a little wider so you can, 6 to 7 and 8 to 8. Another one where the left and right is the same. Similarly, 9 plus 11 over 2 is 10. So we have 9 comma 10, and 10 plus 1 is 11. So we have mid plus 1 is 11, and then our right value is 11. Now let's go ahead and do this first one. 0 plus 1 is 1. 1 over 2 is a half. When you round it down, integer division, it's 0. So you have 0, 0, and 1, 1. Now here, this 2 comma 2. Its left and right value are the same. If you tried to divide it, the mid value is 2, so that means your left would be 2, 2, and then your right would be 3, 2, if you were to make it a parent of 2 children. And that makes no sense. In other words, this is covering the left and the right is the same. So in other words, this is essentially just covering the value at index 2 in the array. And we're going to explain why that works later. To summarize, we just can't split it anymore, so we don't try to make 2 children out of it. In other words, it's a leaf in the tree, aka it has no children. 3 comma 4. 3 plus 4 over 2. 3 plus 4 is 7. 7 over 2 is 3.5. When you round down, is 3. So you have 3, 3, and 4, 4. Notice how we create 2 children over here that have left and right are the same. And over here, left and right are the same. And 5, 5 is already perfectly divided. You cannot divide it any further because it's 5 and 5 are the same. The left and right are the same. Here, 6 plus 7 over 2 is 6.5. But you round integer division down, it's 6. So you have 6 comma 6 and 7 comma 7. And then 8, 8 is going to stay the same because left and right values are the same. And then 9, 10. You divide it. You get the mid value is 9 plus 10 over 2. You get 19 over 2 is 9.5. Integer division, you take it as 9. So that means you have 9 comma 9 and 10 comma 10. And then lastly, 11 comma 11, already done. Can't do anything about it. It's left and right the same. No worries. So notice, as said before, each range we take, that is not what I intended to do, each range we take, we just bisect it. We just kept bisecting it until at one point, one of the left and right are equal, and we couldn't do anything. We couldn't bisect it. Just like in the binary search, when left and right were the same, you determine that you cannot bisect any further. You cannot you either accept that element or say there was no elements in the array because that value was equal to the one that you're desiring. So, same idea here. We cannot bisect it any further. Can people still hear me?
Yeah, we can.
Okay. All right. So that means now we want to do a minimum range query from a left to a right. But instead of necessarily approaching it like taking the range and trying to manipulate it by bisecting it somehow, we're going to use this tree. And every value in the tree is going to have a range. Okay.
I cannot hear you.
You can't hear me? Have I been cutting out?
Maybe it's just on my side because my computer's been buzzing a lot.
No, it's been fine for me.
Okay.
Okay, that's probably just my side.
Yeah, I just realized I forgot to put my Ethernet cable in. If at any point it's chopping up and it's not your end, let me know, and we'll all collectively decide if I need to get my Ethernet cable. So every node in the segment tree has a left and right, as we found out. And now we're going to assign some value associated with it. In other words, like, if we're looking for the minimum range query, then it seems appropriate that for a minimum range query segment tree, we want to find the value that we're going to store in each thing is minimum of range. Oh my god, that was so bad. Minimum of range L, R. So let's start off with the bottom elements here. These leaves that have the left and right are the same. If left and right are the same, then you're essentially asking for, out of one element, what's the minimum element? Like, let's say we're looking at and 0, 0. We only have one element, and out of that range, the minimum element has to be 1 because that's the only element in that range. So that means our value at 0, 0 is going to be 1. Similarly, let's actually copy this. Actually, it's copied with the indexes. Okay. That did not get the indexes very well, but we'll work with it. Similarly, the minimum range from 1, 1, there's only one element in the range 1, 1, and it's the element at index 1. So that means the minimum value out of the range 1, 1 is 3. Let's just fill these in. All right. And same process, 2, 2. There's only one element there. That means the minimum of the range 2, 2 is 7. And I'm going to fill these in because I think that makes sense up until then. 4, 4, only element is 15. 5, 5, only element is 30. 6, 6, only element is 45. 7, 7, only values, only thing there is 16. 8, 8, only value there is 18. 9, 9, only value there is 14. 10, 10, only value there is 6. And 11, 11, only value there is 18. So those are easy enough to fill. Now notice, now that we filled in all the leaves, every parent, if you combine the ranges of the left and right child or children, the total range is going to be that of the parent's range. In other words, I have 0, 2. If I combine 0, 1 and then 2, 2 here, I'm going to have a range 0, 2, which is the same as a range of 0, 2 as the parent. So what can we say about the minimum value of range L, R for any parent? If it's entirely comprised of the left and right children.
Would it be the min of like node L dot value and node R dot value?
And that's exactly correct. That's the biggest thing you need to realize is if it's comprising the entire range, that means the minimum value in the tree out of the range of a parent is the minimum of the left child's value, or the left child's minimum value, comma the right child's minimum value, because the minimum value has to be in one of those segments, because that thing is being divided evenly, or in other words, it's being divided such that all the elements come together and they would combine to make this. So that means the minimum value over here is equal to min. The left child's value is 1, comma, the minimum value over here is 3. So minimum 1, comma 3 equals 1. Similarly, 0, comma 2. The left had a value of 1. The left's value is 1, and the right child's value is 7. So I mean over here, it'd be min 1, comma 7 equals 1. Now let's go to 3, comma 4. Since we're comprising the range, same idea. It's the minimum of, it's either the left child or the right child, whichever value is lower. And obviously, on a good day, 9 is less than 15. And that means that the min of 9, comma 15, 9, comma 15 is equal to 15. So, no, that's not, I did not say that. Pretend that did not happen. Minimum 9, comma 15 is 9, so the value over here is 9. That looks like a weird 9. So of the range here, the minimum value is 9. Similarly, of 9, comma 30, minimum of 9, comma 30 is 9. That means we take, the value here is 9. And let's go up here. This node, 0, comma 5. The left child is 1, the right child is 9. The minimum value is either 1 or 9, whichever one is lower. Obviously, 1 is lower, so that means the value here is 1. Now let's go to 6, comma 7. 45 and 16. Whichever one is lower, we take that one. Obviously, 16 is lower, so we take it as 16. The minimum of 45 and 16 is 16, so we take 16. Similarly, is that an 18? I literally cannot read my own handwriting. That is an 18. Pretend that says 18. Minimum of 16, comma 18 is 16, so that means this parent up here is the value of 16. Similarly, 14, comma 6, minimum value is 6, so we take 6. Minimum of 6 and 18 is 6, so we take 6. Minimum of 16 and 6 for this parent up here is 6, so we take 6. And now, the minimum, finally, this one parent over here, the top parent, the root of the tree, it's either 1 or 6, whichever one is lower. Obviously, 1 is lower. So that means the minimum value is 1. So that's the idea. You split it, calculate it, and then use it for your parent's value. So now we have a range. We have minimum ranges for, we have the answer to certain ranges, such as 6, comma 11, 6, comma 7, 3, comma 4. We have many different ranges, but we don't have all the ranges listed on here. That'd just be way too many to store. So now we have to think about how can we, now that we've built the tree, how can we find the minimum value of a certain range? And our example was 4, comma 10. 4, comma 10. How would we take the minimum range of the values of 4, comma 10? Is that even possible? And obviously, as a hint of spending a lot of time in data structure, of course it's going to be possible, but how? How is the real question is how? And that's what we need to think about. But any questions with how we've built the tree before I go on to explain or give ideas about it? Because if you don't know how to build a tree, I'm going to be honest, you're not going to understand anything further about the segment tree at all.
How do you store the tree?
The tree will be stored as an array, and I'll show you how we index the array. Actually, let's just do that right now. That's a very good question. You can either store it as a node, like you store a node and then you have node left, node right. That's a possibility, But I like to just store it as an array because it just makes things easier to control. This is the general rule for no intersection is root has index 1. In other words, this is the root, so this has an index of 1. And the left child, okay, so if some parent has index v, this is where people get really messy and don't store an index v, and then they just store the nodes, or they calculate the range every time and then have an object with that thing. But this is much easier to understand. If you have some parent with index v, for example, this node with index 1 is a root, but is also a parent of 2 children. This one, this one over here and this one over here. The left child has index v times 2. And then the right child has index v times 2 plus 1. Let's fill that in here. Now that this is actually a very good question. I like to store as an array because it works best, and this is how we store it. So first off, okay, Kevin, you're going to be my test subject, or the person that's going to answer all these left and right childs. So knowing that...
Me or Evan?
Kevin, you.
Oh.
So we have this thing with index 1 here. So what's the left child going to be? Remember, the rule was for every parent, the left child is v times 2, the right child is v times 2 plus 1.
The left child would be 2.
Yeah, 1 times 2 is 2.
Exactly.
And then what's the right child?
It should be 3.
Yeah, 1 times 2 plus 1 equals 3. Now let's go to shoot.
Wait, is this not 0 index?
No, we don't zero index our segment tree. The ranges in the array are 0 index,
Okay.
but the root has an index of 1. All right, Kevin, keep going. You're going to do all of these. Knowing that this index has this is index 2, what is the
4
index
and
of this
5.
one? Yeah, so 2 times 2 is 4, and then 2 times 2 plus 1 is 5. Fill this in.
On the left side? Okay.
Yeah.
That would be 8 and 9.
8 and 9. And then far left,
16 and 17.
16 and 17. Let's go with this
Okay.
5 over here.
Okay, it would be 10 and 11.
5 times 2 is 10. 5 times 2 plus 1 is 11. Now where do we go from here for this 10?
It would be 20 and 21.
20 and 21. Now let's go with this 3 up here.
It would be 6 and 7.
6 and 7. And then this 6, where does this go?
12 and 13.
12 and 13.
Yeah.
And then this 12, this parent.
Oh, 24, 24 and 25.
24, 25. And then this 7.
It would be 14 and 15.
And then this 14.
It would be 28 and 29.
Okay. Now, we see, let's look at this 28. This 24, there's 25, and then jump straight to 28. The reason, okay, Kevin, you're done. Thank you very much.
Okay.
We have 24, 25, and then just jump straight to 28. the reason why there's no data in 26 or 27 is because the node that had an index of 13 is a leaf itself. If it were to be divided further, it would have indexes 26 and 27. But those are not valid points because this thing has a left and right equal to each other, so it's only holding one value, which means it's a leaf. And this is guaranteed to, always work, and there are going to be no collisions, because at every depth we see with like just the root itself, there's only one value, and then with depth 1 or after one division, there's at most 2, and then at most 4, and then at most 8, and then at most 16, and then next row would be at most 32. And the reason of why that's so is because you're splitting one segment into two segments. So there's supposed to be double the number of segments compared to the previous depth. But that's not really important. You just have to know that this will never collide and that this is a valid set of rules for the index to use. But that's the reason why they'll never collide, because you're always going to split, and the sum of values over here, like every row has a maximum of 2 to the power of some values, some number of depth minus 1, I guess, depending on how you think about it, nodes, and that's never going to exceed the total sum, so you'll never get an intersection with two nodes, like let's say this one over here and this one over here, having the same index. Like, they'll never happen. So now that it was a very good thing that Kevin brought that up. Now that we have this tree over here, debating on this, I don't think we'll actually have enough time to go through it, but I'll give a slight idea for now, and then it'll be a challenge for you guys to implement, which I'll make a problem. I'll make a problem where you can submit and implement the segment tree and see if you guys can do it. So let's say I'm looking for, let's go back to this minimum range query of 4, 10. So the idea of a minimum range query to start off in a segment tree is to always first look at the root. And then there's a few cases. The first case is the, let's actually go on the side over here. Cases. For a range of query left to query right, or I usually write as QL, QR, at a node in a tree, with left and right indexes L, R, like the black values, 9, 9, the values that they cover. There's a few cases. First case is case 1. L, R is completely outside QL, QR. Meaning that, like, let's say our left and right of our current node was, let's say 6, 7. For LR, and our QR was like 10, 15. Even though those, okay, let's go with 10, 11. QR. In this case, where L, R is completely outside QR, the value, you cannot use the 6, 7 value because it's completely invalid. It's not in the range. That means you cannot return the minimum value at that with that range. In that case, you just return an invalid value. Or if you're in a minimum range query, just return some really huge value. I'm just going to denote it by the infinity symbol. Return for min value. Because if you return some really huge value that's never going to exist in the array, then that's never going to exist out of all the elements in the array, then you're guaranteed that it will not impact the minimum value of the range QL, QR. So that means that it's not part of the range, its actual value should not be used, so you would just return some huge value so it does not impact the actual QL, QR minimum value. Second case. Let's go L, R is completely inside. QL, QR. Like, for example, L, R is like, let's see one of the nodes from our tree. 3, 5. For L and R. And QL and QR were like 0, 8. QL and QR. If that is the case, then you return node's minimum value. Because now, if L, R is completely inside QL, QR, that means every value inside L, R is valid to use. It should be considered when you're determining the minimum value of QL, QR, of the range QL, QR. So that means that if you just return the minimum value in the range, that means you don't have to search for the children and see if their values, return their individual values, because you know every value is valid, and so you just return that node's stored value, because it's going to cover all the minimum value out of the range 3, 5. And then case 3, in the final case, partially intersect. Or intersect that's freezing for some reason. Intersecting ranges. But not fully. In other words, let's say L, R was 3, 5. And then our QL, QR was, let's say, 4 to 7. They intersect because the values 4 and 5 are both in QL, QR and L, R. But the problem is, if it's not fully intersecting, then there's going to be some value. In this case, the value 3 is invalid in this range. You cannot consider 3, but 4 and 5 are possibly considered. So in this case, you have to actually check the return the minimum value of the two nodes, or its two children. For example, if we were looking for 3, 5, we know its children of 3, 5 are 3, 4 and 5, 5. You want to return the minimum value of the node that has the range 3, 4, or the one that has the range 5, 5. One of the two will be returned. But once again, this L and R is only intersecting with the range QL, QR. So you have to divide that further into its children. And now you only have, this one will be good to go. You just return this value for this node. But this one is now completely outside the range. So you just return some really huge number so that this value gets passed up to the minimum value 3 comma 4, and then and then that value gets passed in the return statement. And then you check which one's less, and then you take that value and return it. So that's the idea. You keep going. There's 3 cases. Either you're completely outside, which you would just turn an infinity value for a minimum value, because that's not going to affect it because it's so high that it's not even possible to reach it. Or and then L, R is completely inside the range, in which you just return the node's minimum value because it's completely valid to use. Or you have an intersecting range, which you check the 2 children, and then you repeat the process for those children. And you return the minimum value that you get from the 2 children, assuming they're valid. If not, you're going to get one of the infinities and then also another infinity. So let's go ahead and visualize that for 4 comma 10. Okay, so actually it's 5:21. I don't know if I want to do it so much today. Can people still hear me?
Loud and clear.
Okay, I'm going to put a poll up. And you guys vote. Do you want me to keep going with this and explain it? Or do you want me to stop? Because this is probably a lot to digest. Just look at the names. Okay, so the vast majority of you are saying stop, which I completely get, and thinking about it more and more. Well, obviously I don't have the perspective of a participant, so I don't know. But, yeah, this is a lot to digest, I would think. So, I'm going to stop for now, and then next week I'll revisit the segment tree, and hopefully finish it up, make and implement, and I'll put up a problem either today or tomorrow, probably tomorrow, maybe even Friday if things get busy. I'll put up a problem for later on where you guys will implement the segment tree in a minimum range query, and I'm not expecting you guys to get it this week because I've only hardly introduced the cases. I haven't even introduced the way you build the tree, but I'll put the problem up on Dom Judge anyways. And if you guys want to have a challenge, you can go ahead and give that problem a try, because I know it's going to be, if for some, especially if for those who are new, who are not really familiar with data structures, this is a lot to take in. It's a lot of work, and it's going to take a lot of casework or understanding to really know what is going on here. But yeah, anyone have any questions with what I've done so far?
Can you ping us when you post it? The question.
Pardon?
Can you?
Oh yeah, 100%.
Yeah. And I mean, I think, is it exam and FSC like due this week or next week?
Okay, so if you go into senior polls, okay, so what's happening is there's some people have final exams or FSCs this week for some reason, but their official exams dates are Monday and Tuesday, and I put a poll up yesterday asking if there should be class. You guys can still vote in that poll, change your mind if you want to. But the exam dates are Monday and Tuesday officially, and Wednesday is supposed to be a day off. So, as of, well, if I'm going with just the polls that I'm saying right now, I'm saying that there will be class next week. But if the polls dramatically change, we won't have class. But yeah, that's the situation. So, yeah. Also because of exams, I unless you have a lot of time where you're prepared and everything, I don't think I don't think so you're prepared to solve this problem with some of the knowledge that you might be missing, which is completely okay. So yeah, I'll put the problem up, put a time limit of like 2 weeks or something like that, just so you guys are familiar with it. Maybe throw in a bunch of some extra hiccups here and there, just so it becomes slightly challenging. But yeah, that'll be that'll be what I'll do. And then next week I'll continue with actually building the tree itself, and how the minimum range query is actually going to work. But yeah, any questions of anything I've done or about club in general or anything?
Yeah, like when you build the tree, like you're putting it into a one-dimensional array, right? So how long do I need to initialize that array?
Okay, yeah, that is also one thing. It's a good upper bound is 4 times the size of your like I dealt with the array with a size 12, right? A good upper bound is 4 times the size of the array of what you're trying to use the segment tree on.
Okay.
What's the difference between the segment tree and the sparse table, like time complexity wise and memory wise?
Okay, the sparse table is really good for only maximum and minimum range queries. It is built in O of n log n. Its memory complexity is also O of n log n, but the query itself is done in big O of 1. But for the segment tree, the building is O of n, the memory complexity is O of n, and the query complexity or the update, the query complexity is O of log n. But in a sparse table, you cannot update the values unless you want to redo the entire thing, in which is going to take forever. So if you have any updating questions, I highly recommend you stay away from the sparse table.
Okay, thanks.
And updating in a segment tree is also O of log n, which we might get to next week.